Chapter 6, Section 1, Attributes of Polygons. The objective of this section is to classify polygons based on their sides and angles. Find and use the measures of interior and exterior angles of polygons. Well, why should we learn this? The opening that lets light into a camera lens is created by an aperture, a set of blades whose edges may form a polygon. Some vocabulary to know. The side of a polygon is each segment that forms a polygon. The vertex of a polygon is the common endpoint of two sides. A diagonal is a segment that connects any two non-consecutive vertices. This means it is not a side. A regular polygon is both equilateral and equiangular. This means that all the sides and all the angles have the same measure. There are two different figures here. We have a concave and a convex. A concave figure can be determined based on its diagonal. If any part of the diagonal contains points in the exterior of the polygon, then it is concave. If you connect these 2 points, for example, notice the diagonal is in the exterior, thus concave. Convex, no diagonal contains points in the exterior of the polygon. A regular polygon is always convex. Polygons have names. These names are based on the number of sides that they have. A 3-sided figure is a triangle. A 4-sided figure is a quadrilateral. A 5-sided figure is a pentagon. A 6-sided figure, hexagon. 7, heptagon. 8, octagon. 9, nonagon. 10, decagon. 12, dodecagon. And for all those uncommon sides, like 20 sides, we're going to use n-gon. And for the example of 20, it would be 20-gon. It's good to remember, a polygon is a closed plane figure formed by 3 or more segments that intersect only at their endpoints. Identifying polygons. Tell whether each figure is a polygon. If it is a polygon, name it by the number of its sides. Let's do A together. In A, we have 1, 2, 3, 4, 5 sides. Notice nothing intersects. It is a closed figure with straight sides. Therefore, we can name this as a pentagon. Take a moment and pause the video and try B, C, and the 2 on the bottom. If you look at B, B is not a polygon. It has an intersection of 2 sides. In C, you see that there is no intersection of 2 sides, and you don't have any curved lines, and everything connects at a vertex. So now let's count the edges. We have 1, 2, 3, 4, 5, 6, 7, 8 sides. That makes this figure an octagon. The 2 figures on the bottom, if you look to the left, notice there's an opening here. It is not a closed figure, so therefore it is not a polygon. On the right-hand side, you have a curved edge. This means this is not a polygon either. Let's get a little more specific. We're going to classify some polygons here. Tell whether each polygon is regular or irregular, and then tell whether or not it is concave or convex. Let's do A together. In A, we notice that 4 angles are each 90 degrees. Therefore, they are all the same. However, 2 sets of sides are different. This makes this figure irregular. The second part of this question asked, well, is it concave or convex? There are no diagonals that you can draw in the exterior of this figure, thus making it a convex figure. Take a moment and pause the video and try B and C. If you look at B, you notice that all of the interior angles here are the same measure, as well as each of the sides. That makes this figure a regular figure. And we know that all regular figures are convex. Looking over at C, notice how all the sides are the same length. However, there are more than just the 4 angles on the tips of the star. You also have these larger angles on the inside. These 2 angles are not the same, which makes this figure an irregular figure. Notice how you can also draw a diagonal on the exterior of the figure. This makes it concave. Let's take a farther look into diagonals. You can use diagonals to determine the sum of the interior angle measures of any polygon. A triangle, for example, has 3 sides. And, well, the number of triangles in a triangle is simply 1. 1 times 180. This 180 came from the fact that we know that a triangle angles measure up to 180 degrees. So let's go a little bit further. If we look at this quadrilateral above, we have 1 diagonal here from 1 vertex, and we notice that we have 2 triangles. So 4 sides create 2 triangles. Every triangle is 180 degrees. So 2 times 180 provides us with 360 degrees. So the sum of the interior angle measures of a quadrilateral is 360 degrees. A pentagon is a 5-sided figure, and the number of triangles is 3. 3 times 180 gives us our 540 degrees. A hexagon has 6 sides, and the number of triangles is 4. So 4 times 180 gives us the sum of the interior angle measures of a hexagon, which is 720 degrees. Well, we can do this with any figure. We have an n-gon, for example. Therefore, we do not know the number of sides, so we're going to replace it with an n. The number of triangles. Look at the pattern that you see. The number of sides is 2 greater than the number of triangles. So, you can take n, subtract 2, to find the number of triangles. Then, just substitute that in for the number of triangles that you have and multiply that by 180. This is the polygon angle sum theorem. Finding interior angle measures and sums in polygons. Find the sum of the interior angle measures of a convex octagon. Well, an octagon has 8 sides, so 8 minus 2 times your 180 will give us our sum of the interior angle measures. Following order of operations, we have 8 minus 2 giving us 6 times 180. And 6 times 180 is 1080 degrees. Take a moment and pause the video and try B. We can use the formula that we used in A for B. A nonagon has 9 sides, so 9 minus 2 times 180, leaving us with 7 times 180, which then gives us 1260 degrees. Now, the difference between A and B is in B it wanted you to find the measure of each interior angle. Well, if it's a regular nonagon, you know that all the angles are of the same measure. So you can just divide your 1260 by 9. And when you do so, you get what each interior angle is. In this case, it is 140 degrees. You can do that with variables. Find the measure of each interior angle of quadrilateral PQRS. Well, you know that it's a quadrilateral, so a four-sided figure. The interior angles add up to 360 degrees. So C plus 3C plus 3C should equal 360 degrees. A little bit of algebra here. Let's combine like terms. We have 3 plus 3 is 6, 7, 8. So 360 equals 8C. Then we can divide by 8 on both sides. And when we divide by 8 on both sides, we end up with 45 degrees. So C is 45. That gives us R and P. So the measure of angle R is 45 degrees. The measure of angle P is 45 degrees. Now we have to figure out the measure of angle S and the measure of angle Q. We can use simple substitution and do 45 times 3, which gives us 135 degrees. And since they are both the same, the other is also 135 degrees. Polygon exterior angle sum theorem. The exterior angle measures one angle at each vertex, mind you, of a convex polygon is always 360 degrees. So, if you look at something as such, notice 147, 81, 132, together they give you your 360 degrees, and it is only coming off in one direction all the way around. Comes from the idea that a circle is 360 degrees. You can do that with a pentagon as well. With your 5 exterior angle measures, they will add up to 360 degrees. Let's try an example. Find the measure of each exterior angle of a regular hexagon. Well, a hexagon has 6 sides, so 360 divided by 6 is going to give you 60. Let's try a real-life application. In this case, a photography one. The aperture of the camera is formed by 10 blades. The blades overlap to form a regular decagon. What is the measure of angle CBD? CBD is on the exterior, if you look at the diagram off to the right. And you know that it's a decagon, so a decagon has 10 sides. Exterior angles all add up to 360 degrees. So 360 divided by 10 provides you with 36 degrees. So the measure of angle CBD is simply 36 degrees. That ends our video on properties and attributes of polygons.